In this second video, we're going to be exploring factors and specifically greatest common factors. And so let's do a quick recap of some things we talked about in the previous section. What you see here are arrays that represent the number 24. And if you take your 24 unit squares and arrange them into rectangles, you really have four different options. Remember, once we get past I refer to it as the squarest possible version, you just start repeating the same factors over and over. So these would be the four options. And the numbers on each side of the array are going to tell you the different factors of 24. This is different from a prime factorization. So if we just write the factors of 24, it's a list. And it would be 1, 2, 3, 4, 6, 8, 12, and 24. Again, 1, 2, 3, 4, 6, 8, 12, and 24. It's all the numbers on each side of those rectangles. Now, if you don't have the arrays, if you're not using those to figure out what the factors of a number are, there's another method that can be helpful. And for me, again, the arrays are so important, but I always like to sort of connect the outer numbers. I think about 1 times 24, right? 1 times 24, and then I go to the next 2. 2 divides 24, so it's 2 times 12. And then 3 times 8, and then 4 times 6. It's like an upside down rainbow, right? So the factor rainbow, there you go. So that's a way of connecting two factors together that would make any of these arrays, right? So again, it's just another way to pair up those factors. So just as a little review, what I'd like you to do is try with the number 20. So just the number 20. Can you list all the factors? Again, not a prime factorization, but just list all the factors. Take a moment to do that. And what you should find is the factors of 20 would be 1. Well, and I'll even do it like this. I'll do the little factor rainbow. So 1 times 20, right, is our first pair. 2 times 10 is our second pair. And then 4 times 5 is our third pair. 1, 2, 4, 5, 10, and 20. There's the list of all of the factors of 20. So one of the things that's important to know is that no matter what type of number we pick, 1 and the number itself will always be factors, okay? 1 and the number itself will always be factors of any number. Now, there's sort of an interesting relationship between the prime factorizations of a number and the factors of a number. And so I'm going to show you what it looks like for the number 15. So the number 15 would be, if we listed out the prime factorizations, the prime factorization is just 3 times 5. Actually, I think I'm going to use a different example for this. Instead of 15, I'm actually going to use the number, and that won't erase for some reason. I'm going to use the number 273. I know that's a much bigger number, 273. But if we did a factor tree, you would find that the prime factorization looks like this: 3 times 7 times 13. Okay? So if that's the prime factorization of 273, we can use these numbers to figure out what all of the factors would be. Remember, factors are numbers that would divide evenly into 273. And so when we start to make the list, if we want to know all the factors of 273, 273, if we list them out, we know 1 is a possibility. We know 3 is a possibility. We know 7 is a possibility, but and 13. But then we start to get into bigger numbers, and there are other factors of 273 besides just the numbers 1, 3, 7, and 13. You can also start to match up numbers in the prime factorization. So 3 times 7, because 3 times 7 is part of that prime factorization, then 3 times 7, which is 21, is also a factor of 273. And you can check, you can divide it, see what 273 divided by 21 is. That same thing would be true for 3 times 13. 3 times 13 is 39, which means 39 is also a factor of 273. And then finally, 7 times 3, which is 91, would also be a factor of 273. Those are all of the different combinations you can make with these 3 numbers, multiplying them in groups. And then, of course, the number itself is also always a factor, 273. And if you look at the different pairs, 1 times 273, 3 times 91, 7 times 39, and 13 times 21 all equal 273. So that's how you can almost build all of the factors once you know the prime factorization. And notice the prime factorization is a lot smaller than when you start to list out the entire group of factors. So what I would like you to try is try analyzing this, and we will do the number, let's use the number 165. Okay, so the first thing we're going to do is do the prime factorization for 165. I'll give you a moment to figure that out on your own. Maybe you did a factor tree. Maybe you said, I know 165 is divisible by 5. Do a little division, and you see that's times 33. 33 is not prime, it's 3 times 11. And so we end up with these 3 factors, 3 times 5 times 11. This is the prime factorization. Now see if you can use that information to find all of the factors of 165. I'll give you a moment to try to do that on your own. So if you think about how we did the previous problem, we know that each of the numbers in the prime factorization, they are, of course, factors. So we have 1, and then we have 3 and 5 and 11. But then we also have to consider the products of these different combinations of the prime factorization. 3 times 5 is 15. So that's a factor of 165. 3 times 11 is 33. So that's a factor. And 5 times 11 is 55. So that's a factor. And then we also, of course, have 165. And so what you'll notice, again, if you examine this list, is that this number is 3 times 5. It's made up of these 2 factors. This is 3 times 11, again, which is 3 and 11. 55 is 5 times 11, 5 and 11, right? So again, you could start to see how even the smaller individual prime factors can be used to build some of the bigger factors. So that, again, is just an important relationship to recognize that exists between the factors of a number and the prime factors of that number. So one of the important things to understand is that type it in here, for any 2 numbers that exist, there's always a number that is a factor of both. It doesn't matter what 2 numbers you pick, every 2 numbers have some common factor. And that's what we're going to start exploring in this next little part of the video. Common factors. And then basically means they have the same factor. And so if I just put two numbers here, 24 and 36, you might just be able to look at those numbers and say, huh, I kind of just know that there's a number that divides both of those. 6, right? 6 is a common factor. 6 divides 24 and 6 divides 36. So that means 6 is a common factor, or you can even call it a common divisor of 24 and 36. So you think of common factors as a number that's going to go into both of the numbers that you are examining. Okay? So we're going to explore this a little bit more. And so what I want you to do now is think about both of those numbers again, 24 and 36. And your job is to list all of the factors of both of those numbers, like we were doing several minutes ago. List all of the factors of both of those. Give that a shot. If you go through the process, what you'll see is all the factors of 24 would be 1, 2, 3, 4, 6, 8, 12, and 24. All of the factors of 36 would be 1, 2, 3, 4, 6, 9, 12, 18, and 36. So 36 has some additional factors. My next question is, what are the common factors? Common factors of 24 and 36. And there can be more than one. So the common factors would be the numbers that appear in both of these lists. So what do you notice that appear in both lists? Well, 1 appears in both lists. 2 appears in both lists. So does 3. So does 4. So does 6. And so does 12. Both numbers have some other factors that they don't share in common, but those are all the ones that they do have in common. And one of the important things that we often try to do when we're examining two numbers is find what's called the greatest common factor. And so the greatest common factor is going to be in the lists that we just made and highlighted which one's biggest. When you're looking at any two numbers, there's always going to be a common factor. And therefore, there's always going to be a largest common factor. And again, we call that the greatest common factor. We often abbreviate it as GCF. So what's the biggest number in the two lists that I highlighted? 12. 12 is the greatest common factor of 24 and 36. And often we write it, because there's always a notation, as this: GCF, and in parentheses, put the numbers that we are examining, 24 and 36, that is equal to 12. And if we want a formal definition of greatest common factor, it looks like this. For any two non-zero whole numbers, A and B, 24 and 36, the greatest common factor, written as GCF, parentheses, A comma B, is the greatest divisor, greatest factor of both A and B. It's the largest divisor, the largest factor of both numbers. So there's a formal definition. So let's examine this in a visual detail, right? Once we start looking at some pictures of these, I think it can often help us see it in different ways. Again, different people, different learners have different ways that are going to resonate with them. So let's look at the numbers 30 and 50. So we're going to explore the GCF of those numbers, the greatest common factor. And so I'm going to share an image here, not that one, this one. And before I even talk about it, just pause and explore it and examine it yourself. What you should notice when you examine this picture is that we've got several different groups, right? We've got this one on top where we've got the number 20 and the number 30. And then we've got this combination of 20 and 30, same two numbers, and then this combination. So we have the numbers 20 and 30 shown visually three different ways compared to each other. So this first one shows that both of 20 and 30 have a common factor of 2. Because if you break up the number 20 into little groups of 2, right? This is like called maybe a rod. You have a group of 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, right? 10 little groups of 2. And for 30, you can do the same thing. And there are 30 groups of 2. So we know that 2 is a common factor. Another way you could do it is take 20 and 30 and divide them into chunks of 5, right? Here's a 5, here's a 5, here's a 5, here's a 5, and then 30 has 2 additional 5s. But that's, again, a length that you could divide into both of those numbers evenly. So 5 is a common factor. Well, this final one shows the number 10. 20, if we put it in groups of 10, there are 2 10s here, and for 30, there's 3 10s, right? So that shows, again, a visual representation of how 10 divides evenly into both of those numbers, and then 10 is the GCF. 10 is going to be that greatest common factor for both of those numbers. So let's try this. Let's try this with a couple numbers. So we're going to do a couple of these. The first one, what I'd like us to try to find is the greatest common factor of 92 and 136. Okay, so we're going to keep in mind the method we just went through, which was start with those prime factorizations so we can see all of the building blocks, right, of the two numbers that we're going to work with. And then we're going to use this fact right here. Look for the minimum number of times that a number, a prime factor, occurs in each of the numbers that we worked with. So if you want to try this on your own, pause. You want to watch another one, then keep going. So we'll start with 92. 92. So I'm going to do a factor tree for 92. That's going to be 2 times 46. And 46 will be 2 times 23. For 136, that is going to be 2 and 68. 68 will be 2 times 34. And 34 will be 2 times 17. So now we've identified the prime factors. I'm going to write those prime factorizations like this. So I'm going to write 92 and 136. I'll start with the 2's. 92 has 2 of them. 136 has 3 of them. And maybe we check them off as we go. And then 92 also has a 23. And 136 also has a 17. I know I didn't put those in order. That's okay. But I'm going to keep them somewhat separate. So my 2's are all grouped here, my 23's here, and the 17's here. So all we're really looking for here are where, again, they have things in common. And you'll notice that they have 2's in common there, 2's in common there, and that's it. That is it. 2 times 2 is 4. So that tells us that the greatest common factor of 92 and 136 is equal to 4, right? The biggest number that divides both 92 and 36 is 4. So let's try another one. So definitely try this one on your own if you didn't do before. We are going to do one with 3 numbers. So let's find the GCF of 14, 34, and 60. So see if you can figure out how you might do it with 3 numbers. So if we do our factor trees, 14 is equal to 2 times 7. 34 is equal to 2 times 17. 60 is equal to 6 times 10, and then 2 times 3, which are both prime, and 2 times 5, which are both prime. Then I'm going to stack them over here. We've got 14, 34, and 60. We have a 2 times 7. We have a 2 times a 17. We have a 2 times a, again, they don't have to necessarily go in order. A second 2, I didn't even stack those very well, did I? I'll fix that. Times 3 times 5. I'm going to, just for the sake of some consistency here, let me remove some of these. Here, I'm going to move the 2 and the 7, or the 7 and the 17 over, just so they kind of look like the other ones we've been doing. Times 7 times 17. All right, so we're keeping our 2's in this range, our 3's in this range, our 5's here, our 7's here, and our 17's here, okay? So again, you might notice they only have one thing in common, that 2, right? They've only got a single 2 in common, which means the GCF is 2. The GCF of 14, 34, and 60 is 2. So you could do this with more than one a pair of numbers. You can find a greatest common factor of 2 numbers or 3 numbers or really any number of numbers. So let's try one more of these, all right? So I want you to try this one. These are going to be some bigger numbers that I want you to explore. And let's find the GCF of 550 and 189. This might take you a minute to go through, but your job is to find the greatest common factor of 550 and 189. Take a moment to try to work through that. So I won't show the factor trees just because I think we've done enough of those. But what I will show is once you get your factor trees done, the number 550 has a prime factorization of 2 times 5 times 5 times 11. The number 189 has a prime factorization of 3 times 3 times 3 times 7. Now, I know I didn't write those stacked like I have been. That can sometimes be a little tricky when you start to get all your spacing. You saw in the previous problem, right? I didn't do a great job of keeping them spaced. It's okay. You can just do it like this and then examine, right? Go through them and say, all right, there's a 2. Are there any 2s in 189? No, there are no 2s. So 2 can't be part of the GCF. Well, what about the 5s? No, there's no 5s in 189. So 5 can't be a common factor. Well, neither can 11. Well, this has a bunch of 3s, but 550 doesn't have any 3s. And it also had a 7, but 550 didn't have any 7s. These numbers had nothing in common. There was not a single number in our prime factorizations that they had in common. So what does that mean then? Is there a GCF of 550 and 189? Well, yeah. If you go back to how we started this, we said that every number has some common factor, right? Every whole number that we're going to work with has at least 2 factors, and every pair of numbers has something in common. If you don't see anything common, what do they still have in common? They still have in common the number 1. Because 550, we could also say, is times 1. We know 1 isn't a prime number, so it's technically not part of the prime factorization, but it's still a factor of 550, and it's still a factor of 189. So that can be the greatest common factor if they have no other numbers in common. We have a name for that. When a pair of numbers has only a GCF of 1, we say they are relatively prime. That's the term we use. 2 numbers whose greatest common factor is 1 are considered relatively prime. And in our next video, we're going to move on to talk about multiples. This was all about factors, greatest common factors, and then we're going to be moving on to